first. So as you know, AI is extremely popular these days in different applications, including healthcare, self-driving car, different chatbot. Such popularity in these AI technologies have raised several security concerns, which is basically the focus of today's talk. So one of the major challenges we face in the practical deployment of these AI models, particularly deep neural network, a popular form of AI, is performance, efficiency, privacy, and security issue. Today's talk, I want to basically talk about the security side of the problem, which basically deals with how safe these AI models are, can a malicious attacker cause havoc in its functionality. So before understanding the security challenges, let me first explain the components of deep learning. A deep learning component has training data. It has a model or the algorithm that deals with the training data. So after training, we get a set of equations or formal set of equations, which basically defines the behavior of the model. Now next, the model goes into the deployment phase where evaluation happens with future test data, hoping that the model is performing accurately as expected. If not, that's called misclassification or performance. So in this overall flow, we have two key components. First is the data that goes as input to the model. Second is the model itself, which has a set of parameters, weights, biases, and the topology architecture. The security threats primarily comes from these two parts, data and the model. How? So first, the attacker can manipulate the input to cause harmful behavior at the output. Second, the attacker can actually cause model perturbation, disturbing the model weights to achieve the same kinds of behavior. The third one is backdoor Trojan attack, which basically modifies both the input and the weights to get these kinds of harmful behavior. Let me go into a little bit of details into the backdoor attack. Backdoor attack basically inserts hidden behavior into a clean model so that the model attack performs benignly when there is no input trigger. But whenever the attacker design trigger is present at the input, the model basically misclassifies to a target class. Now, today's discussion is about our paper in ICCP 23, which basically deals with source-free domain adaptation, the impact of backdoor attack in source-free domain adaptation. So to understand this paper, first we need to understand what is source-free domain adaptation. Domain shift is a popular phenomenon in practice where we train with a set of data sets. We expect pretty reasonable accuracy on that set of data sets, but when we test with new incoming data where there is a distributional shift, for example here, the background changes, the model performance drops significantly. To solve this problem, different domain adaptation techniques were introduced. So let's look at them. So in typical domain adaptation technique, the source has labeled data, and then the target owner adapts the model to a new target datasets and finally tests it on the new target datasets. But in source-free domain adaptation, one condition must be imposed. That is, the source trains this source model. The target owner cannot access this source model. So taking that source model, the target owner can only train with the target dataset and improve the performance on this new domain of distribution. So what is a security challenge in this source-free domain adaptation? We asked 4 key research questions to investigate that. What if the source owner is malicious or an attacker? Is current SFDA method secure against backdoor attacks? Can they actually pose security threats to the target application? If yes, how much protection existing defenses provide? To investigate the first three questions, we need to define a threat model. This is our threat model. Our threat model's assumption is source owner is the attacker who can access source training, source model, source dataset, and has label, but cannot touch the target training, target model, target data, or target label. On the other hand, the target owner, who is the victim or the defender, cannot access source training, can access the source model where the target training starts, cannot access source dataset or label, can access target training model and dataset, but again, they don't have any label data. Based on these assumptions, we attack the source model using backdoor attack. Three popular forms of backdoor attack. The results is obvious. All of the attacks gets 100% attack success rate on a source dataset. RW just defends one kind of domain. Now, once this model has been taken by a target owner, and then they adapt it to a new kind of domain, let's say AR domain, the attack success rate is still significantly higher. This observation concludes that SFTA is not secured against backdoor attack. Given a malicious source training, the target model is also extremely vulnerable. We applied all the existing defenses, state-of-the-art existing defenses, and the result was obvious. Most of the defenses require label or source data to perform their analysis on the malicious model, which that's why they don't directly apply in this current setting. One defense we could apply is a data-free technique, that is CLP defense, that actually could reduce the attack success rate, but with significant cost of accuracy or benign performance. So the answer of the board research question is the source owner is malicious, causes disaster at the target application. The current SMT method are not secure. A source threat can pose a severe security threat. And finally, existing defenses fail against this protection. So that's where our proposed defense comes in. The research problem we're dealing with to defend is how to make SMT secure against backdoor Trojan attack. Here is our goal. What we observed so far is a source owner inserts malicious behavior into the source model. Now a new target owner tries to adapt that target model to a new application. The source owner achieves success by getting benign performance correctly, but whenever they insert the trigger, the model goes to a target misclassification. Our objective would be we take the same source model, but train it in a way so that the source owner fails in their objective here, making a defender happy. But we have few challenges. First, we cannot access source datasets. That's why all the defenses fail. Second, our training needs to be unsupervised. There is no target level. Third, we cannot train the classifier because typically in source-free domain adaptation, the classifier remains untrained. So how can the target owner overcome these challenges? We propose two possible solutions. First, the target owner needs to adopt data-free techniques for defense. And the target owner has the training phase, which needs to be utilized for the defense, which none of the prior defenses actually utilized. So our proposed method consists of two components. First is static component, where we take the source model, prune certain channels from that model. Those can potentially contain some backdoor information. At the second stage, we dynamically train the model with a new loss function to remove regrow of those previously pruned channels. So how do we know which channels are malicious? We basically take spectral norm as a measure of sensitivity in the model. We measure the spectral norm of every channel in the model and prune the ones that are above a certain threshold. This threshold can be tuned, and the performance of the defense, of course, varies with the selection of the threshold. But the problem is, pruning reduces model accuracy. Now, once you prune those channels, the model performance goes down. That's why we propose to keep an auxiliary target model as a backup. The job of this target model would be to generate accurate pseudo-level, because this prune model cannot generate accurate pseudo-level for our training. So the purpose of this auxiliary model is to support the training of the compressed model through generating accurate pseudo-level. The second component is dynamic backdoor suppression. We basically propose a training loss function that will ensure during training, those suppressed channels remain suppressed, cannot grow as the training progresses. However, there is one challenge to computing spectral norm during training, because this basically means you need to divide the matrix into its SVD form, which is expensive computation. So we propose an alternative computation of the spectral norm for training. That is basically a spectral norm of a matrix is basically upper bound by the trace of the A transpose times A. Hence, we use this upper bound to compute the spectral norm during the training and apply the loss function. After applying the loss function, we expect the channels that we eliminated, hoping to eliminate the backdoors, will remain eliminated as the training process progresses for the target domain. The result is as expected. This basically shows the attack across several domains. A, D, W is basically referring to 3 different domains. So source is A, D is the target domain. Here, source is A, W is the target domain. You could see across all the combination of source and domains. Conventional SFDA is extremely vulnerable with high attack success rate, and our proposed SSDA could reduce that attack success rate while maintaining proper clean accuracy. If we compare with state-of-the-art all the SFDA techniques, we observe that across the board, the attack success rate remains higher. Our proposed method achieves the best attack success rate with on par clean accuracy. That's what this figure shows. Basically, if the performance is at the bottom, it's secure range. On the top, it's a vulnerable range. On the right, it's a well-performing model. In an ideal world, we expect the model to be here, where it's extremely secured, extremely accuracy, but that's highly impractical. Our one is on par with the existing defenses methods, but is in the secured region of the spectrum. Finally, we have 3 different components, right? One was compression, second was knowledge transfer from auxiliary model, third was the dynamic compression. So the baseline defense is extremely vulnerable. After we add our compression, the model's attack success rate goes down, but at the expense of accuracy. To recover the accuracy, we propose that knowledge transfer, basically keeping the auxiliary model, which successfully recovered the clean accuracy, but still not good enough attack success rate. Then we propose the dynamic suppression during training to further suppress the attack success rate. In summary, if the source model is malicious, that behavior transfers into the target domain. Our proposed 2-component training techniques, static completion and dynamic pruning, actually helps suppress the backdoor behavior from the source model to the target domain, achieving the attacker's desired success. In summary, source-free domain adaptation, we believe, is the future of deep learning because of the popularity of large language models and lack of training data. Security of the adapted model is under severe threat from our initial observation. So we expose this security challenge by successfully injecting backdoor into the source training for the first time. And our proposed solution is the first defense against malicious source owner, providing protection to the target. That would be all. Feel free to post your questions. Thank you.